So thank you all for being here. So let me start by avoiding a confusion. So on the program is written that David is the speaker, but he couldn't make it. So he asked me to replace him, and the good news is that probably you won't see much difference because he's my twin brother and he looks pretty much identical to me. The bad news is that whereas he's an expert on quantum information, I'm not very much an expert on quantum information. However, for this talk, I think it shouldn't matter too much because it's mainly about an application of convex optimization. I think it for sure will be interesting also to this audience, or I hope at least. So let me start also mentioning the co-authors of this work. So it's joint work between me and my brother David, and then also Peyman Mohajer and Esfahani, that is with the University of Delft, and John Lygeros from ETH Zurich. So, okay, now let me start with the talk. So I start with a quite basic setting, that is we have an infinite sequence Y that is induced by some moments, mu. And now we ask ourselves, so this is a classical moment problem. Given such a sequence, does there exist a measure that induces these moments? Now this is a very classical problem and has been studied in the literature, and probably many of you in this audience know much more than me about that. So for different settings or support sets of these moments, it has different names and has been studied in different contexts. So if it is, okay, we restrict ourselves for simplicity to the real line here, but then if it would be a compact interval, it's known as the so-called Hausdorff problem, moment problem. If it is the full real line, the Hamburger moment problem, and if it's just a positive real line, the Stieltjes moment problem. Now, and in the literature, there are exact statements on when such a moment exists, like conditions on the Y sequence. Now, even more interestingly, so once we know, let's assume the data is given such a moment exists. Is it unique? And it turns out that in the Hausdorff moment case, or in the compact support set, this is always the case, and in the other two settings there are sufficient conditions such that such a moment mu, such a measure mu is unique. Now, the reason why I list this as an introduction is because what we are interested in this talk is that the sequence of moments that we are given is finite. So we have a sequence that goes from 1 to capital N, and now we make an assumption, so this data is somehow consistent, so it was generated by some hidden distribution or probability measure mu, and the question is now, how could we estimate or find a probability distribution or density that would induce this given moment data? And of course, to many of you, this is obvious that in general, since we have a finite sequence, there are infinitely many probability measures that induce those moments. So now a natural question would be which one to pick. Which one is an informative one in some sense? And there is many applications, and we'll maybe come to one in the end of the talk if I have enough time, that suggests that a natural or good candidate oftentimes would be to pick a probability measure that first induces those given moment data, and on top of that maximizes the entropy. And this is what we are gonna, and so now in this talk I'm gonna try to lay out like an algorithmic structure how to numerically find such a entropy maximizing distribution or density.
Is this what's called a max-end principle?
A max entropy?
Max-end principle, there's something about
Yes, so the solution to that is sometimes in the literature is called like the max-end distribution or max-end density. Yes. And so, okay, so we write this in a little bit more general form, which is like instead of just maximizing the Shannon entropy, we go and minimize the so-called relative entropy between mu and the reference measure nu. And now the constraint that you see on this optimization problem is just the consistency with the data. So it should induce like the given moment data. And we optimize over the space of probability measures on a support set K that is a subset of the real line that I will later assume to be compact in our set. Here it is. Okay, so I assume that it is compact. Now, if we go to a special case where the reference measure nu is the uniform distribution on K, then actually the problem here on top reduces to the classical max-end problem, right? Like maximizing the differential entropy subject to the given constraints, and under these assumptions, or in this particular setting, one knows that the optimizer is unique and is even a density. Okay. So now I want to make this setting a little bit more general. This is also why in the title it's called like generalized maximum entropy setting. And it will be as follows. So we assume that our data, y, that we get, it could be somehow corrupted by some noise term, which is modeled via this ui here, which lives in a set calligraphic ui that I assume also to be a compact and convex subset of the real line. And now I also need an assumption that the zero element is in this particular set. Now, a few definitions, but after that I guess it's pretty much non-technical. So I define the set T, which is just the product of all these subsets that are listed here, which is then a subset of Rm. And I define a linear operator that brings me from non-negative measures on K to Rm, which is defined as following. It's just this linear integration operator here. And with these two notations, I can now write down the problem, which is the one that we are going to find a numerical algorithm to solve, which is this generalized problem here. Where I have, again, I have slightly rewritten the problem, so we take the minimum with respect to all probability measures supported on K, and then the objective function is the relative entropy between mu and the reference measure nu, subject to this linear constraint. So operator A applied to mu should live in the set T. Now, okay, so now here comes a wish list. So this problem in general is quite hard to solve numerically because there are several issues. The first one, which might be the most obvious one, is that this
what is the role of
nu,
yeah.
It's a reference measure. So you could imagine in this particular, you can always imagine it to be the uniform distribution on K, and then this problem is just a classical max entropy. Yes. So I mean, we put it just to be a little bit more general in the setting. And we will later have some assumptions on nu such that it works. So not every nu works. Now, and this is probably also now one of the more important slides in this talk. So the goal of this presentation, or we would like to have three properties on an algorithm that can numerically tackle this problem. The first one we want to achieve some epsilon optimality. So our goal would be to derive or come up with a J epsilon that is epsilon close to this J star, which is known to be a hard problem. But okay, there is more properties that we would like our algorithm to achieve. A second one is like a feasibility. So usually, or in many settings, we are not only interested in the optimal performance, but also in an optimizer, or achieving an optimizer. So we would like to find somehow a probability measure that I noted here with mu epsilon that is feasible with respect to this convex optimization problem. And on top of that, if I evaluate the objective function, it achieves me this epsilon optimality. And the third one, okay, this has to be understood in quotation marks, so tractability. So I will come later to that and make all these properties more formal. So we would like to have an algorithm that runs efficient in whatever sense this is. And we will see that some of these three wishes we can achieve, but not all of them. And some we have to weaken a little bit later in this talk. Okay, so now here's a rough outline how we tackle this problem. So very roughly speaking, we try to invoke this particular structure of this problem in a smart way. This is kind of in a nutshell, what is going on. So first, we slightly reformulate the problem. That will be quite a trivial step. Then in a second step, we dualize the problem. And probably some of you have seen, so the underlying idea behind that is that we have a finite number of constraints because the set T was in Rm, right? So these constraints can be understood as finitely many. And now when you go to the dual, you will have like the dual variables will be finitely many. So this is the underlying idea. However, then when dualizing the problem, you will see that this problem enjoys a very particular structure that we try to invoke. And seeing this structure, we can use some recent developments in convex optimization literature, which is known as the so-called smoothing techniques that allow us to introduce a regularization term to make the problem a little bit nicer from a numerical algorithmic perspective, and then apply what is called in the literature fast gradient method that usually runs quite fast. And then I will show you what type of error bounds we can achieve. And hopefully I will come back in the end to these three wishes that I stated in the beginning. Okay, so let's start with the first point, with the rewriting the problem. So I have summarized the general problem here on top, not to forget it. And now what I do is I just introduce, I rewrite the problem very slightly. This is a trivial step. So what I've introduced is this sigma t, which is known in the convex optimization literature as a support function. So it's nothing else. So in this particular setting, sigma t of c is nothing else than the maximum x in t of the inner product between x and c, which in this particular setting is just x transpose c. Now, this is really a trivial step, and now we can see, okay, what I have already mentioned, that the difficulty with this is called, I call this the primal problem. The difficulty here is that the optimizer mu is infinite dimensional. Now, a natural idea would be just to dualize this problem because it's a convex optimization problem. And then the underlying hope would be that the dual problem and the primal problem share the same objective value, which we will have to prove later. So let's try to dualize that. And since we don't know yet whether this will have the same value, I call it JD, the optimal value. And now what I basically did, just interchange like min and the supremum. And now, if we look at this dual problem a little bit closer, I see that now the dual variables are finitely many. And I call the dual function, I denote it with capital F of C. And if I had, now let's imagine I had access to this function F of C. This would be a finite dimensional optimization problem, right? So this would be, let's say, numerically tractable with whatever method we would like to use. In our case, a gradient type of method. So this is the underlying idea. Now there is several difficulties with this approach. So first of all, how to express this dual function f. The second one is, okay, if we can express it, how would we use it? So it turns out that this f, as it is written here, is not smooth. So we cannot use like a gradient method as it is. And the second one, which is, or the third one, which is also quite interesting, is that the problem here the optimizer, the primal optimizer, has this nice interpretation as this max end density or max end probability measure. And now, if we solve here this dual problem, is there some way to, like track back the primal optimizer? So this is another thing we have to keep in mind when blindly using this dualization approach. So, okay, so let's now jump into the dual a little bit more closely. And let's first try to convince ourselves that they have the same value. Or in other words, like there is zero duality gap between the two optimization problems. This is quite easy to prove. This is, one just invokes standard results in the literature. It's basically a consequence of convexity as well as the compactness of our support set. So those are the two key ingredients that are used in establishing the zero duality gap statement. Now there is a further statement if we have what is called a strictly feasible point, or in convex optimization literature a Slater point. We know that these dual variables are even more like compact, live in a compact set. Or in other words, so this C can be restricted to a compact set in the Euclidean space or M. Okay, so now now what I will address next is how to express this dual function f of c efficiently. And here I make a small digression about the result that I guess in this community you are all familiar with, which goes back, if I'm not wrong, to Gibbs, which is that this particular optimization problem here, like the minimization of the relative entropy with an additional linear term, this has a unique solution, and is given here. So this is even though it's an infinite dimensional optimization problem, it's nice because it has an analytical solution. And therefore, now, if I rewrite this dual function, I can see that if I here just, all I did, just use like property of the linear of the adjoint operator, I see this red term here is exactly what is like the Gibbs term. So I can analytically express that. And okay, here in the box I have the optimizer, but if I plug in the optimizer, I get like this Gibbs solution, which is this minus log of this expectation term here. Now, this is, I guess, a quite nice result because it's a smooth function when we look at it as a function of c. And so this is quite nice. So the problem is with this support function. So this is a non-smooth function in general. And this makes our life from algorithmic or convex optimization point hard. So, okay, so I have, and now, okay, so the idea is now how to deal with this non-smooth part. Is there a way to add a regularization term such that this problem becomes even nicer to solve from an algorithmic point of view? And this is inspired by a chain of works that was, I guess, initially branded by Nesterov and then other of his co-workers and other people. And the idea is that, okay, first of all, let me try to say that what is the problem because this f is non-smooth. So the problem is that in general you cannot use a gradient method. What you have to use is a so-called subgradient method. And those are known to be very slow they have a very slow convergence rate. And the second difficulty with this function that I didn't discuss yet is that in order to numerically find a primal optimizer, we need what is called like a strong concavity of this function f, and that's also not there. So if you would analyze this function, you would see that it is concave, but not strongly concave, and this is also needed. Therefore, the idea is the following. So we introduce a small regularization term. So eta is a two-dimensional positive vector that we will show later how to choose it. So it should be chosen small, but not too small. And then I slightly modify this dual function f, and I call it f eta. And what I've introduced is here a term here that makes the support function term like smooth, and here a second term which gives me the strong concavity of this function f. Now, if I look at this function, it's quite easy to see that now this modified function has the properties that are most desirable from a gradient, from a numerical perspective, which means like it's strongly concave, differentiable, and even smooth in a convex optimization setting, which is understood as that the gradient is Lipschitz continuous. This is extremely desirable from an algorithmic perspective. And the Lipschitz constant, which will later be used in our algorithm, can be also quantified explicitly. It's given here. And you see here the Lipschitz constant blows up if this regularization term is chosen too small. So now the idea is now that we, instead of solving the original dual problem, we solve this so-called smoothed dual problem, which is I replace f with f eta. And I can solve this type of problem with the fastest first-order methods available for this class of problems, which are fast gradient methods. And even more, I will show you that using this modified problem, I can reconstruct a near-optimal primal optimizer. The question that remains to be answered is how to choose a eta. So what would be a good candidate? Because clearly, if I choose eta too large, this problem here that I'm solving is too much different from the original one. And in the end, what I want is an answer to the original non-smooth problem. And if I choose it too small, this regularization term, you have seen, for example, this Lipschitz constant blows up, and the problem kind of gets a non-smooth problem. Okay, so here I have summarized again in a nutshell what is going on here. So the original dual problem is a non-smooth problem, so therefore one would need so-called subgradient methods which have a provable computational complexity of 1 over epsilon to the 2 in number of iterations. So this is complexity number of iterations. Now, the class of strongly concave and smooth problems, they can be solved in 1 over square root of epsilon. And our problem that we have lies somewhere in between. So we have to apply the smoothing technique. So we will answer a problem that has a particular structure. So this is required of the type 1 using the methods of type 2. And what we will come up with is a computational complexity that is in between. So it's 1 over epsilon plus this logarithm term. So this is the rough idea that is going on here. Now here is the algorithm. That is very easy. So if you haven't seen that, doesn't matter. So what is going on is a kind of two-step algorithm, which is called in the literature of like a fast gradient method. Here we have like the gradient of this smoothed function, and here is the Lipschitz constant that I've mentioned, and then there is a second term that is needed. Yes. So yeah, that is quite easy to implement. I also want to say that. Now there is one last assumption that I need to, in order to establish like the explicit error bounds that we want later, which is, I've already mentioned it, which is a type of a Slater assumption. So I need to assume, and I will show later that this can be quite hard in practice later to find such a Slater point. But for the moment, let's just assume that it exists. So there exists a mu0, which is a probability measure that is feasible, and even more is kind of strictly feasible. So it's delta, delta much in the interior of this set T. And this delta parameter will later come into the game to determine what is the optimal smoothing choice for the smoothing parameter, which comes here. And here I apologize, it's a bit a mess. So don't need to understand all of that in detail. So I define a few constants that depend mainly on this Slater point and a few other parameters, such as the diameter of my set T, etc., etc. Then I have here, I choose an epsilon, which is a non-negative number, which gives me the precision that I'm interested in. Now, based on that, I give you the two optimal choices of these regularization parameters. And then here there are two other numbers, which are telling me how many iterations I need to run of the algorithm that you have seen for an epsilon precision. And here is the result. So let's quickly go through it. So for any given epsilon that I choose and the parameters that are defined here on top, if I run n epsilon iterations, where n epsilon is the maximum between these two numbers here that are easy to evaluate, then the algorithm produces the following two variables. First, it produces like a near optimal dual variable, which I call C hat, and it also provides like a primal epsilon closed primal optimizer, which is mu hat. Okay, they are defined as follows, and now they have the following three properties. So first, it holds like that there is dual epsilon optimality. So here the 0 is just the weak duality. That's trivial because this is the dual problem. But it shows that if I evaluate this dual optimizer here, is epsilon close to the J star. Now, for the primal, we have a very similar statement. So there is just here a constant and also the epsilon. So it shows that this optimizer here is also very close to primal optimal. Now, how about the feasibility? And this turns out that this is a little bit hard. So this primal variable mu hat here is not necessarily feasible, but it's very close to feasible in the following sense. So this here is just a distance function on Euclidean space, and it shows that if I evaluate the operator A with mu hat, and the distance function to the set T is at most a constant times epsilon. So, and on top, so I would like to mention that those are like a priori guarantees. So I choose epsilon, my precision, and then this theorem tells me how many iterations I need to run. But it provides something even stronger. And in practice, this matters a lot. So it provides also a posteriori certificate, because we have like this optimizer C and mu hat, and this I've summarized here. So once you have like this primal and dual optimizers, you can also plug them in and you get this term here, which is a so-called posterior certificate. And you will see in a second in numerical simulation that this turns out to be much, much smaller than the prior bound. So in practice, this is really a nice feature that this method also provides. So now very quickly to this Slater point condition that I mentioned. So it can be, so how do you find this mu0? And this, I have to admit, can be a challenging task. So in this particular setting, there's different ways how one could compute or guess such a mu0. One is just, okay, look at the problem and try to guess a candidate. The other thing is try to use, for example, a polynomial approximation that would just solve like a feasibility problem. I don't want to go into details, but you can really solve, you fix a degree of a polynomial and then you try to find a polynomial that is feasible and gives you a feasible candidate. This is also what I've used in the simulation. It works, but okay, in general, you can always say you don't know what is the degree of this polynomial. You need to somehow, like increase the degree of the polynomial until the class of polynomials is rich enough such that you can find a mu0. So here is a numerical simulation that could give some insight. So I've chosen a distribution, and I'm not going to tell the algorithm, so it's hidden. And I've generated the first 3 moments with this distribution, which turn out to be this number here. So the supported is the 0, 1 interval. And now I run the algorithm for a given precision epsilon and for different choices of my uncertainty set. So this optimizer here, so this U here, these moments here, could be additionally perturbed with an element of this uncertainty set. And now you see if the uncertainty set is chosen very large, which is this blue line, I basically get like the constant thing, which is the maximum entropy density it's a uniform density. However, you see then later when we make this uncertainty set smaller, we are somehow centered around like the real maximum entropy density. And now maybe this is also interesting, which is a numerical table for 2 choices of small uncertainty sets. And let's go to this one. So I've chosen here, what I fixed is this a priori error epsilon. And now you see, so those are the posterior upper bounds and lower bounds of the capacity. And you see that those are roughly 1 magnitude smaller always than the prior bounds. So the posterior bounds are 1 magnitude smaller than the prior bounds. And this is how many iterations we need to run of this algorithm. Here you could see how this scales with 1 over epsilon times this logarithm term. And here you see the posterior feasibility certificate. So it turns out that we are lucky, and with this number of iterations, it's even feasible. Okay. So now you could ask yourself, so because the problem in the very beginning, it looked quite difficult. So it's an infinite dimensional optimization problem that in the literature has been studied already a lot and is known to be a difficult problem. So this looks all kind of quite nice in terms of computational complexity. So where is the difficulty hidden? And it's hidden in the evaluation of the gradient. So I tell you here how many steps of the gradient we need to run. And the infinite dimensionality is hidden in the gradient evaluation. So this is the fundamental part of the gradient that needs to be evaluated in each step. And it turns out that here, if you analyze this a little bit more carefully, is an integration hidden. So this is a parametric function in terms of C, which is the dual variable that we are optimizing over. So somehow you need to evaluate this often. And this, particularly if you go to higher dimensional settings of K, can get challenging. However, I would like to claim or say that maybe the contribution of this work could be seen as follows. So you take an infinite dimensional optimization problem that is known to be very hard to be solved numerically. And what we provide is a method to transform the difficulty into a numerical integration. And for numerical integration, we have a lot of tools available that in some cases work extremely well. So for example, this type of integral, because it's like exponential of a polynomial, they have been studied in a polynomial optimization setting. So there exist like semi-definite programming approaches to approximate those things, because that's also the point that I would like to mention, that these gradient methods are usually quite robust. So even though the gradient has a small error, it usually doesn't matter for the convergence of this numerical scheme. So I would also be fine if this is just approximated. And therefore, these semi-definite programming methods are quite powerful. And there is other tools. So a student in our group has tried to use quasi-Monte Carlo methods and Gauss quadratures that are specifically tailored to these approaches, which work quite nicely. Okay, so now let me actually come to the last part, which is a small application that shows in my community what is an important application of these maximum entropy densities. But there are many others. So I know that in recent years, there have been many machine learning approaches and techniques that rely on these max end densities. So I think the potential range of application of this problem is quite vast. However, this is something that I've been interested a little bit in the past, which is called like a stochastic chemical reaction. So assume that you have like a small chemical reaction and that you want to understand how many species or molecules of each particular component are produced. And this is modeled oftentimes in a stochastic setting. And then you're trying to estimate what is the density or the distribution of each particular component, which is given by what is called like the chemical master equation, which is a particular instance of the Fokker-Planck or Kolmogorov-Forward equation. Now, and oftentimes we can say, okay, we don't want to know the full distribution of each molecules, but what we are fine is if we know the first, let's say, 2-3 moments of this distribution. And in terms of moments, this chemical master equation can be written as follows here. So M denotes is a vector of moments up to a certain order that you have fixed, capital M. Let's say the first 3 moments. Now, this is an ODE, but unfortunately, so there is a dependence on higher order moments. So this is a linear differential equation or ordinary differential equation. It has the problem that these zeta moments are higher order moments. So it's computationally intractable. It's an infinite dimensional object. Now, since the problem is so important, particularly in chemistry and engineering, people have come up with approximations to that. And one idea is the following. One idea is, let's try to guess what is called like a closure function, which is an analytical expression that tells me how the higher order moments can be expressed in terms of lower order moments. So you guys know, for example, for the normal distribution, we know that higher order moments can all be expressed as functions of mean and variance. And so there is a closure function in the moments. In general, this is not true, and you introduce an approximation. And this I try to summarize here. So let's assume that we can somehow guess or find a so-called closure function, which gives us an expression of the higher order moments as a function of the lower order moments. And then this ODE that I have here on top can be expressed as the following ODE, which is not linear anymore because in general this phi function might not be linear. However, is now a finite dimension, so it's now something that can be solved numerically. So the question here is, there is 2 open questions. One is, what would be a good closure function? It's highly problem specific, but is there a generic way of finding a closure function? And the second one is, this is a nonlinear dynamical system, so how about stability of this? The second one, to the best of my knowledge, is still unsolved. And the first one, there is a lot of work and numerical evidences that using the max end principle as a closure function is a very nice candidate. And this now closes the gap to what we have done. So I tried to explain you now what is called like the zero information moment closure method. So this is the following. So I again write down here like this ODE for this function phi, and now try to explain you what is a good candidate for phi. So here is the problem that this talk was based about. And let's assume that the optimizer of this, I express it as mu m star. And the m is important because the data points in T that used to be denoted with y are now m, that I have written here. So here you see the T, so what I have replaced, so the y's are now the m at a given time. And nu I choose the uniform distribution. And now the zero information closure function is nothing else than just evaluating the optimizer here for higher order moments. That's all that is going on. Now, this has been simulated a lot in the literature, and it turns out to work extremely nice. The problem with the approach from a practical perspective is that finding this mu m is hard. So one reason why this method is not used extensively is because it is computationally difficult to find these max end densities. But however, if we have an efficient method to find those, this would be a particularly useful application because you need to evaluate these max end densities at all time instances. So if you have a type of Runge-Kutta scheme that solves this ODE, at each time step you have to solve a max end problem for given moments. Here is a small simulation. So a very small reaction, like 2 molecules of type M react with a rate constant K1 to molecule D, and then you have the inverse reaction with a different rate constant, and then we have a simulation for different rate constant ratios. And now the solid line is like what is called stochastic simulation algorithm. This can be assumed to be the optimal solution. And then here we see how our max end or zero information closure system gets closer to the optimal solution as we increase the order of the closure system. Okay. So with that, I come to the conclusion. And this I would like to do the conclusion with this wish list that I had in the beginning. So I have tried, or I've given you one particular way of numerically dealing with these type of optimization problems in the box. And we have seen that the epsilon optimality can be achieved. So this is something that is clearly doable. The feasibility, okay, here I guess our answer is mixed. So what we can do is find a mu epsilon that gives us up to constants this approximate solution J epsilon. However, the feasibility, we have to be happy with a epsilon close feasible solution. Now the tractability, okay, here, okay, either you make the cross or the check mark in the bracket because, okay, it's tractable under the assumption that you can deal with these integration problems. So, okay, up to you whether you color this in red or green. And yeah, with that I would like to conclude and thank my collaborators and leave the room for discussion.